This is the first of the forums that we'll have over the next few days, but with that, we'll get going. So I'm Brent Frizzell. I work for Specialty Coating Systems. My role is supporting automotive and electronics, so it's industrial electronics and everything sensor related. So really looking at that promotion. Today, we're going to talk about how do you design a sensor to survive in corrosive environments. So when you look at the design of the sensor and then how do you make sure that that device is going to last, and what conformal coatings do for that overall design. So what we can expect, so really looking at just the challenges that sensors face. So really, what are the environments that are going to be a problem that might cause them to fail? When you look at the impact, so like if a sensor were to fail, what is the problem there, right? So what is going to be the detriment or the big challenge? Next, when you're looking at when do you evaluate coating? So when you're talking about the design process of a sensor, when in the design phase is best to look at coatings? How do you align with industry standards? So when you look at a sensor design, it's going to have an aligned, whether it's automotive or it's going to be, say, medical. There's sensors have different designs. How do coatings fall into that? And then we'll get into exploring the different types of coatings and what might work for sensors and the different applications. So where are sensors? So sensors are everywhere. We're at a sensor show, right? But we're really talking about where you might find them. So more in like robotics, cars are going to have more sensors, talking about the safety of driving and the autonomy of driving. You look at, say, industrial sensors, so pressure sensors, temperature sensors are going to be things that are growing in the marketplace, as well as smart cities. So you talk about 5G connectivity, talking about increasing numbers of outdoor sensors in the environment. So challenges sensors face. So when you look at what environment you're putting the sensor in, that's something that you'd want to look at. How do you protect from it? But you got to know where you're at first. So challenges from humidity. So that might be hot environment, say in a coastal area, or it could be just a hot environment. Say like I'm from Indianapolis, Indiana in the States. In the summers, it gets very hot and very humid. Others are moisture. So you talk about morning dew from the air. You talk about things maybe from coming in contact with water from maybe different processes and environments. Moisture is probably the most prevalent challenge you're going to see with sensors. Extreme temperatures. So you're going to be putting sensors somewhere into hotter environments or colder environments than others. So how do you design the sensor to be protective from the, say, moisture and humidity, but also survive in a higher temperature environment? So also looking at how do you protect against corrosive fluids? So you talk about gases. So maybe if you're in the oil and gas market, the H2S gas is very corrosive. How do you protect from that? And really those also gets into the harmful gases. So what do sensors prevent? So sensors are there to really help things like safety. Maybe in a medical, it's really helping to keep someone healthy, alive, and alert. But also like in automotive, it's preventing crashes, right? So sensors are all around us, but they're really designed to help, say, automate and improve, but also improve overall safety. So when you're talking about designing a sensor, you want to design a sensor that can last. So you're really, maybe you're designing it to last 5 years, 10 years, 15 years, but overall you want the sensor to survive in that environment. So when you talk about designing the sensor, we talked about the different challenges that the sensors might face in the environment. That could be electrical issues, could be moisture issues, or corrosion issues. So when you look at, say, with respect to coatings, the different coatings have different properties, and I'll get to that a little bit later, but you're really looking at what might be the right protective barrier for my sensor. And then when you look at the different testing, so if you're, say, testing 2 or 3 different types of coatings, you'll run through, and typically the right coating will come to the surface. You're going to have the right coating technology that's going to help to design the designed life expectancy for the sensor to last. So when we talk about conformal coatings, when do you actually want to look at designing? When do you want to actually test? So this gets into the overall design and the cost of a sensor, but ideally you would test in the R&D phase, right? So you're testing R&D, you're proving out based on the different test parameters, environments of the sensors that you're testing. It's going to be most cost effective to prove it out in R&D. Then when you get into the next phase, right, you're looking at, say, the early phase design. So you're maybe in automotive, you call it kind of the A testing phase, which is going to be evaluating different materials. But at that point, you're going to be able to really pinpoint what is the right coating. You don't want to wait till the product's ready to go to market. And then that's going to be a real challenge to maybe redesign, have to recertify, and a lot of different things that would add a lot of costs to in the short term when you're trying to launch a sensor or launch the products. So really another thing is conformal coatings are well aligned to the different industry standards. So whether you're in aerospace and defense, you're in automotive, or you're going to be in, say, medical, conformal coatings are designed and the processes are designed to support the industries that you're in. So let's take a look at conformal coatings. So different types of conformal coatings have different properties, and they're meant for different applications and different environments. So if you're only talking about, say, a moisture barrier protection, pretty much a lot of conformal coatings, almost all of them, have some layer of moisture barrier protection. But if you start saying I need corrosion barriers or I need electrical barriers, then different coatings may not work so well. So you talk about an acrylic coating really isn't one if you're looking for electrical isolation protection, isn't really going to work well. But if you move into, say, like a parylene, or even say, I'll talk about kind of an enhanced ALD parylene combination that gives enhanced barrier properties. So it really looking at, again, we talked about the challenges, what environment your sensor is going to go into, and we can start to look at what is the right coating again for the application. So just a quick hit on what is a conformal coating. So it's very, very thin. So you're talking about like on the micron level typically, or maybe even into the nano coating level. But it's typically non-conductive. It's going to be a dielectric layer, but it's providing a barrier property. So whether it's electrical insulation, moisture barrier, chemical barrier, that's really what the design of the different types of coatings are. And in the marketplace, there's several types of coating. So you get into parylene, which is vapor deposited. You get into plasma, which is also a vapor deposited coating. But then you get into, say, some liquid applied coatings like acrylics, epoxies, silicones, as well as you get into, say, some nano coatings. So there's a lot of different types of coatings that are out there in the market, and it's helping to guide to what is the right coating for your sensor based on your needs. So one of the major barrier properties that you're going to look at for coating is electrical isolation. So you talk about electric vehicles today, they're really looking at how do we isolate high voltage systems from one another in very close confined spaces. Also looking at the design of electronics, they're getting smaller. So you're actually protecting the communication in the boards from the different components that are on specifically. So when you look at electrical protection, the coatings themselves have been tested at many ranges. Frequencies are one thing that could be potentially impacted. Really, the low dielectric constant of the material has little to no impact on the design of, say, a radar sensor in the market, say for a car or maybe for industrial applications. So protection from moisture and humidity. So what we're showing here is a test that was called a salt fog test, which is going to test a corrosive, humid environment, say in a coastal region. So you think about electronics, if you go to a coastal region, you're going to see metal is going to be corroded more. It's harder to keep things in the condition that they were when they were designed. So this is showing a parylene coated electronics, and this is one that was uncoated, right? And the parylene coated one looks like it just came off the factory floor. So really looking at the design and going through the testing, but this is a very common one. It's also tested with, say, halogen-free variants that are going to be designed again for what we're looking at for what is coming from, if you're familiar with PFAS, but it's looking at the design of materials to be halogen free, specifically unfluorinated applications. So another moisture and humidity, you could get into plasma coatings. So when you look at plasma type coatings, they're going to be very thin. They're going to be on a nano scale. So you could be on a very, very thin, sometimes for just moisture resistance, right? So we're not talking about full on barriers, but just a very thin film to maybe say disperse the water. They have a very high contact angle. So it's very good for dispersing water off of the surface. Plasma coatings are very common in consumer electronics as well as medical, say like hearing aids and applications like that. So chemical resistance, so we talk about corrosion, so designing to prevent from corrosion. One of the best properties, so with Parylene, is the chemical barriers that you're going to see. So I've talked about some different coatings. Parylene is very, very good and resistant to chemicals and corrosion. So when you're going to look at that, it's not going to be, if you pour a solvent on there, it's not going to dissolve away. It's actually very, very resistant to that. So it makes it a good application. And again, I'm going to get onto the next slide. It kind of shows it, but you can get into some different gases, right? So really, I say H2S gas, if you're going to be, that's a very, very corrosive gas that you're going to expose to, and kind of shows these are different types of acrylics, epoxies. So acrylic would be one that you wouldn't necessarily use, but it's talking about how long does it take for that gas to permeate onto the surface that it's protecting. Also showing on this side, it's showing the different types of coatings and how the water vapor transmission rate. So coatings, there still is a transmission, but again, how long does it take for the water at a unit thickness to penetrate? So another type of coating is you can start to get into multi-layered coating. So think about layering a cake. If you're going to stack them one on top of another, you're going to have, say, the Parylene on one and the ALD on the other. It provides even more enhanced barrier properties. So on the last slide, I was showing water vapor transmissions rate for just Parylene itself. But when you add it with, say, a small amount of aluminum oxide ALD coating, that you get an even better, higher performing water vapor transmission. So you might see these on fully submerged things, like say if you're into Bitcoin, this helps to keep those systems around. Also sensors that go in subsea. So you're talking about sensors that are designed to be on like offshore oil platforms. These are really a good application for that. So also looking at not just the water vapor transmission rate, but also the gas barrier and the permeability. So if you look at with the combination, you can just see how the numbers and the performance grow. So depending on how critical the device is, maybe the sensors, the criticality of it needing to perform, sometimes you would go with, say, a more enhanced coating like ALD plus Parylene. Finally, when you're looking at like choosing a coating, different coatings have different temperatures that they can withstand. So if they're going to be put into, say, an environment that's 350 degrees C, there's coatings that will last and are designed to stay and maintain their barrier properties in that given temperature range. So you could get into low cryogenic, you could also get into higher temperature ranges. So in summary, there's a lot of sensor applications in many different markets and different environments. I'm really looking at designing them early on to have the right protective coating to make the sensor last in the design, say 10, 15 years, whatever the design criteria is for the sensor. So there's a lot of coatings. You can align the right one that's going to fit your need, again, whether it's a moisture barrier or chemical barrier or electrical isolation, there's going to be the right coating for the sensor. So with that, any questions? Do you have a microphone? Yeah.
Okay. We are working with tiny MEMS sensors, and we are trying sometimes to code these sensors, the sensing element.
Yep.
We tried Parylene, but we had issues that after the first protection was perfect, but after some time we got some little spots where the Parylene was not
adhesion issues.
Yes, and so we could protect the sensor for maybe for days, for weeks, but not for years.
Right.
And what experience do you have with such kind of long-term elements? So we measure density of gases and liquids. So a small change in the sensor behavior and changes our calibration and so.
Yep. Yeah. So really, you're looking at is adhesion. So it's the material that the coating is adhering to. I can say that we have proprietary, but in the market, it's adhesion promotion. So you're looking at how do you, so it's like making sure that first off, that it's clean. So the cleanliness of the surface is critical to making good adhesion. There's also adhesion promotion materials that will make it easier to last for a long time. So like Parylene, for example, is designed and tested to last for 10, 15 years. Typically, it's not going to be the first thing that fails. If it's applied properly, proper adhesion is done. So that would be something that, we would look at. And when you're doing, again, why I say testing in the R&D phase is you work through those issues, right? Sometimes it's not something that you're just going to have the first time. We all would like that to happen. First time solution works. Yes. But that would be, we looking at the cleanliness and then what type of adhesion promotion was done on the sensors. We've coded a lot of MEMS technology and had a lot of success in that field. So that would be something that we could look at.
Okay, thank you.
Yeah.
What's your footprint in Europe?
Yeah.
How do you support European sensor customers?
Yeah, so we have 5 sites in Europe. So we have coating facilities that are all across Europe, all across the world. 21 sites. We have a site in Switzerland. We have a site in Germany, site in the Czech Republic, Ireland, and the UK. But we also, all of our sites have kind of grown to support customers. So there are instances if there's large customers that we have actually built new sites in support. So looking at that way.
You kind of focused on Parylene coating, but you showed a slide earlier with all different types. Do you offer all of these coating?
Yeah, we offer the full coating. Not every site has each coating. Okay. Every site does have Parylene. Okay. It has those machines. We're expanding our footprint into liquid coatings. We have that primarily in the US and the UK right now. Okay. The plasma coatings we have in Europe, US, and in Asia. So we're expanding and growing that the ability to be closer, and that's something that we work with customers. And the testing phase, it's a little easier to ship parts further, but then we understand the proximity relationship and supporting the European market specifically.
Okay, thank you.
Great question. All right, with that, I appreciate the crowd getting started, ready to go this morning. And we're the ones that had our coffee. That's what I would say. We're ready to go. But appreciate it and enjoy the show.